So we're doing, I don't know if you guys realize, we're walking through the elements. The original elements were solid, liquid, gas, or earth, water, air, and fire. Fire is the transformative. So today is actually Earth Day. So we're doing the earth element, or solids, which could not have planned that better if I had tried. I didn't realize until today when I saw the Google Doodle is really good today. So if you get bored, you can go look at it. I was really excited. I thought it was going to be a game. And so I was going to send you out a bonus, but I almost will probably find it. Last year when we were, several years ago, the best Google game ever came out, and it's a gnome catapult. And you put gnomes in the catapult, and you have to, I'm terrible at games. I've been banned by my son from ever playing video games, but this one, so anyway, my students, it was an extra credit, and people got addicted to it and it came out last year again during COVID, during one of the weeks of total quarantine. Google every day had a different one of their games. And so I was hopeful today, but it was just a fun little video. All right, this is all about solids, and there are so many different shapes these can take. This is all going to be geometry. So what I'm going to tell you is this page is not going to make a lot of sense. Just take notes. And as we get into the math on the next pages, we will keep referring back to this. So this is kind of the intro. But the idea with the cubes is that the atoms always touch. So on a simple cubic, you would have, these are supposed to be circles. Your lab next week, by the way, so week 5 folders there for next week. So it's going to be a rainy day, Saturday and Sunday. So if you guys have to has anybody started their presentation, their research? You have to have 2 studies, remember. So it's going to be a rainy weekend, but if you want, you can also start this lab. It's not due until the next weekend, but it's all math. So if you're inspired, but the idea is, this is a simple cubic. So this is one face. This is the face of the cube. So we're just looking at it from one side. So think of a dice. So there's 6 faces on a cube. And so we're looking at one face, and what it is, this is a unit cell. So unit cell goes from the center, the nucleus, and it fits in. So these parts of the atom are part of that unit cell. Only the parts I'm coloring in. The other parts are part of another unit cell. So almost nothing is going to form a unit cell that looks like this, because that wouldn't make sense for atoms to stack up one on top of each other like that. They're going to form the other ones we're going to talk about. But that's the idea. That's some of the terminology we're going to see. So we're looking at a face of the cube. The cube is 3-dimensional. And so there's 4 different positions in the cube. And we're going to go through this math. Again, this seems very esoteric initially, this part, but that when an atom, if the atom is in the corner, like it is here, you actually have one atom. So it's because there are, on a cube, how many corners are there on a cube? So think of a dice. Get a new name up here.
4.
8.
Oh, 8.
There's 8 corners, right? Because the top and the bottom of the cube. So there's 8 corners, and so this is a corner. You'd have to have a bunch of dice, but if you stack the dice like one on top of the other in front, that this atom is part of 8 cells. So there's only 1/8 of an atom per corner. So every atom is part of 8 different cells. So you can see there's, like, this would be part of another cell, this would be part, but then there'd be 4 in front of it stacked up. So you can do it with boxes or dice or anything that's like basically a rectangle cube, times the 8 corners. That's where I get 1 from. This funky math that we're doing right here, when I tell you to show me like your work, how you figured out how many atoms there are, this is what I'm talking about. So you guys get your notes, and we're going to do this enough that you just kind of know it. All right, the next one is a face position. So these pictures here are actually really nice. This shows in 3 dimensions what a simple cubic would be. And again, the actual cell would just be the center of each one going back to the one behind it. And back there. So that's our simple cubic. Did I do that right? Maybe. This is a face center. So what a face looks like when you have, this is a face position, would be this guy I'm coloring in purple, is if you think of a dice on a face, if you had dice next to each other, the face, you would have half of an atom per face. So if there was an atom on the face of the cube, half of it would be in this unit cell and half would be in the unit cell in front of it or next to it, whichever direction the face is going. And there are 6 faces on a dice. We're using regular dice, not like the 12 or 20 sided dodecahedron, 16-sided ones. So you have 3 atoms. So a face position is 3 atoms. I think I have better pictures on the next pages. I do. That's showing you a face. So this is showing you a unit cell. I should have brought the one in from school. So see this is, it's cut to 1/8 of an atom at every corner. But you have 8 corners, that adds up to a full atom. And then this guy, he's been cut in half, or this one at that face. So there's 6 faces, and every face has half of an atom because the other half of the atom is in the next unit cell. This one's a really easy one because that's a center position. And when an atom is in the center, it's in the cell. The whole thing's there. So you have the full atom, meaning 1 is in the unit cell. And so that's going to happen here with that one. This atom here is in the center of the cell. These other ones are the corner positions. All right, the other possibility, and these up here might be, oh, that's not what we want. None of them are showing the edge. So to be along the edge of it would be that you're like here in the middle. You're not in this at the corners, you're not in the center, you're not on the face. And there are how many edges on a cube?
8. 12.
There's 12. There's 4 on top, 4 on bottom, and the 4 connecting. So there are 12 edges. Who said 12? Not going to tell me who said it. All right. And you have 1/4 of an atom per edge. And that is, again, that every edge touches that. So most students take the attitude, I'm not sure I fully understand what she's talking about, but we get to these numbers that this is going to be 1 atom, this is going to be 3 atoms, this is 1/4 times 12, we get back to 3 atoms. Because it's going to always tell you if you're at an edge, a face, a corner, or in the center. And then when you're asked to show this, like on the lab, you just copy exactly what we just did there. Or as we go to the next pages. So before I leave this page, so everything on the periodic table, all these metals, all the solids form some way the atoms stack up inside of them. And These are actually all the different possibilities. They form some really interesting, elaborate shapes. We are not going to do anything with rhomboids. So you guys remember back like in whatever grade, 6th or 7th grade, when you did geometry, or 10th grade, you had to do, right, of different prisms. We're going to do everything with a cube, which makes it really nice, because if you're dealing with a cube and you're dealing with the volume of a cube, it's always equal to the side cubed. So we're not going to have to do the volume of a rhomboid or the volume of the hexagonal prism and stuff like that. So that's going to make our math really simple. And so yeah. All right, let me find my next page. So is this the next page? It is. All right, so apparently I wanted to talk about face-centered and bodied-centered next. I have my notes from last year to see if there's anything else I should say. I had colored notes last year. All right, so this is what face-centered looks like. That's showing how they would, and the key here is how many atoms are there. So you have the face and you have the corners. So the corner is 1/8 of an atom times 8 corners. So we get 1 atom. And the face is that we have 6 faces times 1/2 of an atom. So again, this is trying to show you it's cut in half like that. And so when you add this together, that gives you 3 atoms, that you're going to always get 4 atoms per FCC. So for most problems, when we're solving it, you're just going to use this number. There are places, though, like in the lab for next week. Again, there's no lab this weekend because you guys are preparing for your presentation and your paper on your molecule. And it's never too late until actually Tuesday at 2 o'clock to change your molecule. Just send me an email and say, hey, can I switch to this? All right. And remember, you want to make sure you talk about 2 scientific studies and talk about the data. You don't have to go into terrible detail, but you should have a solid slide about it and have some discussion about it. All right, now we're going to talk about the relationship of an edge, or the length of a side, and I'm going to use the variable a, because if I use L or S, if I use an S, people think I write a 5. If I use an L, people think I write a 1. So we're going to use an A. That's why everybody in the books do it. And the radius of the atom, which is R. So the problem is, if you notice, there's a gap there. We'll just call it the gap. How can we measure from here to here without knowing the gap? And this is where our good friend Pythagoras, remember Pythagorean theorem? We're going to do that. So this corner to this corner here, this diagonal, there's no gap. The atoms touch along the diagonal. So the diagonal, remember a squared plus b squared equals c squared? You don't have to write that down, but that's considered one of the 10 most important formulas of all time. A and B are the same, right? So my A, these are my A's. So these are the same because it's a cube. And then C is the diagonal. Just so you can follow my math. So we basically here have 2 A squareds. And then this is going to equal the diagonal squared. And along the diagonal, how many radiuses are there? Well, we have 1. We have 1 up here. And then going across the whole diameter is 2 more. So we have 4 radiuses. Does that make sense? So going from this corner to that corner, going across the diagonal, or what they call C, there's 4 radiuses. So each edge, and then across that whole one on the face. But we have to square it to make our friend Pythagoras happy. All right, we're going to make this simple. We're going to make it we're going to get rid of the square root. So we're going to move it to the other side. So if we take a square root of both sides, you'll get the square root of 2 times A equals 4R. And I'm like boxing it because we're going to use that when we get to the next page. So this is for FCC. You are not going to have to go through this. I go through it because there are some of you, it really helps to understand where these formulas come from, where this number comes from. So that's why this is, all I'm doing here is showing you where that number comes from. Now we're going to do it again for BCC. So we're pretty much going to do 2 types of cells. We're going to do a face-centered, where an atom is on the face, which means the atoms touch across the face, or we're going to do a bodied-centered. Now, bodied-centered is interesting. You have one atom in the center, and then you have one atom at the corners. And that, again, comes from you have 1/8 of an atom times 8 corners. So this ball here in the center is completely inside. So we're going to have 2 atoms per BCC. So you can see what you're going to want to do with this. You're going to want, well, actually, if you have it circled or highlight it, because these pieces that I'm trying to, maybe we should put pink. My pink doesn't work. Maybe that's why. All right, now we're going to do the relationship here. And this is the one that's really cool. The atoms touch because you can't have gaps. It's a smaller gap, but we have to go from this corner all the way to that corner. So not the front corner, not along the face, it's got to cut a corner. And so if you go from here all the way through to this corner back here, there are 4 radiuses. The full Pythagorean theorem is that the length squared plus the width squared plus the height squared. So basically, if we go this diagonal this way and this way, you would get the body diagonal squared. So most of us never learned that one, but the Pythagorean theorem was a 3D formula, or it is a 3D formula. These are all the same because we're working with a cube. So we basically have 3a squared. So a squared here plus a squared there plus a squared there, we reach to that equals the body diagonal, which is our 4 radiuses squared. So we do the square root again, and you get the square root of 3 times a equals 4 radiuses. And so this is for this formula we're going to be using. Again, you don't have to derive it. I just mentioned that. I guess I gave you room so you can make sketches and stuff. Oh, that's fascinating. I did it exactly the same way. All right. You guys don't have to memorize anything, but one of the things to realize is this was 3-dimensional to get from one corner to the other. So that's where 3 comes from. And this was 2-dimensional because we're only going on the face. So that's why it's just a 2. Wait, if you like relationships. This picture here is showing you where they're not touching. It kind of looks like a dice. This is showing you if it kept expanding. Your unit cell would just be like this repeating unit. FCC is the most common because it's how you would pack things. Like if you were packing stuff, you would put balls, you would make them pack like that. The BCC is a little bit more complex, and it's hard to see the full cell, but you can always pull those up like on the computer and look at them too. Or you can go on Google and they'll have ones that they rotate and stuff. So to do the math, there's 4 variables. There is R, which is going to be the radius. There is I'm going to say D, or rho, which is going to be the density. And this is, again, of our solid. There is what the solid is. So the molar mass. So grams per mole. If we know the molar mass, then we know what it is. And then there's the type of cell. So this is either FCC or BCC, because it's going to determine if we do the square root of 2 or the square root of 3. So those are our 4 variables. I'm going to always tell you if it's FCC or BCC. So you can see that in these 3 problems that we're going to do, it tells you FCC, BCC, BCC. So you're always going to want to find that piece and underline it. This one tells us, we'll just walk through it, that we have aluminum, and it tells us the radius is this, and we're going to find the density. So the lab, you guys basically have 2 weeks or a week and a half to do the lab. It's just a lot of math calculations. So when you have time, just do it. Don't wait until like next Sunday, because next Sunday might be like this beautiful weather. Really depends on how your classes and everything else lay out. So if you have open time this weekend because you didn't go to the beach, then you can crank out the lab, or you can wait and do it the last minute next weekend. All right, you gotta get your paper done, your presentation. So if you're told what it is, start with that. So we're gonna start with the fact that it's aluminum. And we're gonna have a couple steps. Well, we can do it all in one, but what we know about aluminum from the periodic table is aluminum is 26.98185. So 26.98 grams per mole. This is going to be factor labels, so we want to get to atoms. How do I change moles to atoms? Get your name up on the board.
Is it Avogadro's number?
It is Avogadro's number. 6.022 times 10. Do you guys remember that number? Times 10 to the 23. It's in the denominator on this, so remember you want to use parentheses, and that is atoms of aluminum. And we're going to take it one more step. This has to do with the previous page. So this is FCC. So the question is, how many atoms per FCC unit cell? You can say just per FCC, or FCC is the unit cell. Some people like that better. And so we figured out FCC is 4 atoms. So that is our number there. It is a whole number. It doesn't affect this. Now, if you want, you can find out what that number is, punching in your calculator. That is going to be grams per unit cell. I'm going to do this as one big setup because I'm in that mode right now. So my moles canceled, my atoms canceled, so we're there. We're trying to solve for density, and density is mass per volume. So we're going to be grams per cubic centimeter is what we're trying to find. So we have to find the volume. So up here, this is our mass. This is like our step 1. And down here, we're going to find the volume. So that's kind of our step 2. And then we can just bring the 2 together. So take the 1 and divide by the other one. So the volume for all of these, let's just write it up here, they're all cubes. And I already mentioned that the volume is always equal to A cubed. So we have to get to A. Well, that was what the point of this was. It's FCC, so we're going to use this formula. Square root of 2 times A equals 4R. So you can state the formula over here. So square root of 2 times A equals 4R. So always state your formula. We want to rearrange it to solve for A. So 4 radiuses divided by the square root of 2. That is our A. So this is A. You can do this one of two ways. So you might want to pause for a moment before you write this down. How I do it, and there's going to be a couple of you can do this. You're going to recognize this is A. You can just cube it right there. And you're like, I'm good to go. I can do it like that. And then you would just take the mass divided by the volume. Or some of you, you're going to want to like solve it for A. And then once we find A, you'll do A cubed equals the volume. And then once you have the volume, you'll do density is going to equal the grams divided by the volume. So that is fine. You can do it as one big step, or you can break it into steps. Just make sure you label and say what's going on. So even if you do it as one step, you have to state your formula so I can follow what's going on here. I'm going to go ahead and do it as one step because I'm writing too big to do it in multiple steps. But there's nothing wrong with breaking it into steps. Just make sure that your steps are either numbered or labeled logically. All right, so we're going to have 4 times the radius. The radius is 1.432. What's that A with the halo mean? Angels? That was over the square root of 2.
Angstrom?
Yeah, that's our angstrom. We need to be in centimeters. So nobody saw where we were going with that. So density is grams per milliliter, or grams per cubic centimeter. So we have to change our angstrom. Anybody remember what an angstrom is? I just remember that nice chart you had. Actually, there's angstroms 10 to the negative 10 meters is an angstrom. And then centimeter, either 100 centimeters in a meter or 1 centimeter is 10 to the negative 2 meters. And again, you're going to know based on your math skill when you punch this in. I actually do have numbers. So let me write the numbers down. So if you want to try and punch it in, or actually let me give you, and then you're going to have to cube this. So you can find this, and then you're going to cube it, and then you're going to take the top divided by the bottom. So I'm going to pause. I want to give you guys like 2 minutes to resume recording. Keep punching in. So again, you can do it all. Some people are, oh, I lost my answer key. For the top part, if you punch it in by itself, you should get 4 sig figs, because everything has 4 sig figs in this problem. So 1.792 times 10 to the negative 22 grams per unit cell. We're dividing by Avogadro's number. That exponent's going to be really important. When you punch in this bottom part, so before you cube it, in case you broke it into steps, so if you just figured this part out, you're going to get 1.432. That's not right. I don't know what that number is. I know what it is once you cube it. So 6.645 times 10 to negative 23. Because we're multiplying by 10 to negative 10. We change it all to centimeters, and that is centimeters cubed. And then you put the two together, and we should get pretty close to 2.7 4 sig figs, though. So 2.697 grams per cubic centimeter. So the lab, this is actually what you guys would have been doing in lab. This is always a really fun lab because it would be second term and you're actually pretty good in lab, and people would get really, you would actually find the density, and then we would figure out how close you got to the actual, and this is from doing the math.
Sorry,
All right.
so we got the 6.645, and then we divided the 1.792 by the 6.245. Is that what we did?
Yeah. So this number divided by that. Yes. This divided by that. Yeah. And again, if you want to just do it as one setup, you can. But for most of us, we're going to want to break it into 2 steps. And all right. Anybody else question on that one? So on number 2, we know it's vanadium. We know it's BCC, and we've got the density is this. So we're trying to find the radius. We know it's vanadium. That's where you're going to start. So since it's vanadium, 50.94 grams per mole. And then Avogadro's number. So 1 mole over 6.022 times 10 to the 23 atoms. And then it's BCC. So 2 atoms per BCC. And then we're going to go one more step. So we got rid of the moles, we got rid of the atoms. We actually can change our grams to centimeters cubed by bringing in the density. So we're going to divide by the 6.11 grams to 1 cubic centimeter. All right, this is going to give us centimeters cubed. So that's our first step. And we'll break again. I'll give you guys a moment to either go drink water or try punching it in. Our second step, anybody see what our second step is going to be? We're trying to find the radius, which is one-dimensional. This is the volume. So you're going to take the cube root. So you can either say taking the cube root or taking the volume to the 1/3 power will give you the length of a side. So you can either write it as a cube root or to the 1/3 power. It's however you like doing it. I do it like this because it's easier, the type of calculator I have. That gives you the length of a side. And then your third step is it's BCC. So using this formula here, the square root of 3 times A is going to give you 4 radiuses. And then you're going to have one more step. Your fourth step is, you're going to change it from, it's going to be in centimeters, and I want you to try changing it to picometers. Pico is 10 to negative, we'll see if you remember, but see how far you can get. I'm going to pause it unless there's a question. I'm going to have you try and see, work through it. You're still working on it, just keep going. All right, so when you punch this one in, our density is going to limit us to 3 sig figs. So 2.77 e to negative 23, and our units are cubic centimeter. So that's our first step. Then we take the cube root of that. And you should get 3.025 times 10 to negative 8 centimeters. Now, something I want to point out, you are going to always see certain exponents. When we are in centimeters, you're going to find that these things are really small, that if you're getting an exponent, once you get to one dimension of 10 to negative 8, you're probably doing it right. So it's just, you'll start seeing that number as you do more of these. And then we put that number in here. This is A. So the square root of 3 times that number, 3.025 e to negative 8 centimeters. And then we'll divide by the 4. That will equal the radius, which is 1.31 times 10 to the negative 8 centimeters. All right, we still have one more step, which is centimeters to picometers. So centimeter is 10 to the negative 2 meters, and then 10 to the negative 12 meters to 1 picometer. And that's where I got my answer of 131 picometers. So I usually either ask for picometers or angstroms. So those are really the only two metric besides centimeters that we'll run into. Questions? All right, we got one more on this page. So it's BCC, so that's good. There's our radius is 126, and there's our density. We're going to try and figure out what it is. So we can't start with what it is because we don't know what it is. So we're going to start, I'm going to start with the radius. And if it's BCC, square root of 3a equals 4 radiuses. So this is going to be my first step. So 4 times my 126 picometers divided by the square root of 3 will equal my A. So that's my step 1. And since only the 3 that you're doing a square root of, that should give us 291 picometers. Before you cube it, you want to get it to the centimeters. So 291 picometers. We're going to change it to centimeters. And then your third step, this is A. You're going to do A cubed to get to your volume. That's going to be in centimeters cubed. Once you have centimeters cubed, you should at least be able to get to grams. The unit you're trying to get to, and I'll walk through it, but for some of you might be able to figure it out. We're trying to get to grams per mole. So this is technically cubic centimeters per unit cell or per BCC when you find this step. So when you do this step 4, it's going to be a little factory label step. It's going to be that you're going to start with the centimeters cubed, get to grams per unit cell, and then see what you can do from there. Or per BCC, and then you can change your centimeters to grams and then play with it. So I'm going to pause again, let you guys play with it for 2 minutes. If you're working on it, keep going. I'm going to walk through. So our first step, we got our 291. And then we're going to change it picometers to centimeters. So picometer is 10 to the negative 12 meters. And then, so these are really the 3 different ways of solving. So the first one was solving for density. This is solving for radius. And this is, if you have the density and radius, how to find what it is. And then 10 to the negative 2 meters to 1 centimeter. And if you did it right, you should get 2.91 times 10 to the negative 8. So like I said, when we get to the realm of centimeters, 10 to the negative 8 is because they're all similar enough in size. Then we take that number and we're going to cube it. So 2.91 e to the negative 8. And we cube it and we get 2.46 e to the negative 23 cubic centimeters. So any questions? And then we're going to take that number. So that's our number here. We're going to put that as our starting point down there. And our density that was given in the problem, 7.874, that's up here given in the problem. And that gets rid of our cubic centimeter. That gets us to grams. We want to keep the grams. We don't want to change that. So the piece we want to cancel out is the BCC. And so what we know is there are 2 atoms per BCC. But this time the 2 atoms is on the bottom, the BCC is on top. And then for the atoms, Avogadro's number, this time on top, over 1 mole. So kind of keep that in mind that, so on your study set, the second page is just 3 problems. And so they're similar to this. And find your flow. Don't just sit there and copy, try and figure it out because that will be more efficient. That crosses out atoms and we should get to, oh, I wrote a question mark there. I wonder why. 58.4 is what I got. Did somebody else get 58.4? Okay. And then you would look at your handy dandy periodic table and cobalt's 58.9, nickel's 58.7. So I'm going to go with nickel because it's slightly closer to nickel. So nickel. We're good. Does anybody know how you could tell in lab with a really simple way if it's nickel or cobalt? If you had a magnet, just a regular magnet, cobalt is magnetic. Oh, is nickel? I don't think nickel is. Iron and cobalt are, oh, nickel might be too, so maybe that doesn't work. All right, never mind. One more page. All right. So, ionic solids. This means we're going to have a cation and an anion. Almost always, the anions are at the corners. And that is because the anions are negative. So they, right, when they gain electrons, that increases their size. And so the larger atom is at the corner. So the anions just assume the corners and the cations fit in the holes. So I know on your worksheet you have cesium chloride. So cesium's in the center and the chlorides are on the outside. So I want to mention that. So for the cesium chloride, normally for BCC, we say there's 2 atoms, but there's 1 cesium and 1 chloride because the 2 atoms came from, sorry, I have to keep flipping around here. On a BCC, there's 1 in the center and 1 at the corner. So in this case, the cesium's at the center and the chlorides are at the corner. So what that means, though, when we do the math, and you'll see down here, we're not going to do it for cesium chloride, is there is technically not 2 atoms per unit cell. There is technically 1 cesium chloride per unit cell, because there's 1 cesium and 1 chloride. So the numbers might change slightly. And that's for if it's BCC. For sodium chloride assumes an FCC. So the chlorides assume the FCC and the sodium, that's down here, this picture. So these would be the chlorides, the big ones. And then these are the sodiums, are the little white balls. And so they're in the holes along the edges, and then there's 1 in the center. So we're going to do an FCC calculation. And you are either going to be told one of 2 things. You're either going to have to figure out if the sodium fits, like the cation fits in there. You're going to have to be told, we're going to have to do the math different on these. And so there's an assumption that's given, like on the worksheet for the cesium chloride, and it says, assume that they're touching still along that diagonal. That's not true here, because if you look, there's going to be a gap. So the sodium is just a little bit too big, and when we put it in here, it pushes the chlorides apart. So it's going to change our math a little bit. We're actually going to do this one with sodium bromide because the one on your lab is with sodium chloride. All right. And I gave you up here, we have the radius of bromide is 196. So it's FCC. And what we're going to try and figure out is that space, the gap. So in an FCC, esoteric kind of, this is an FCC. So these would be the bromide atoms. What we're trying to figure out, let's go ahead and write all the bromides. We're trying to figure out how big of a space there is between from here to here. So that's the space. So any ideas? We know the radius. It's FCC. So right now we're assuming it touches. So if it's FCC, 4 radiuses equals the square root of 2 times A. We're going to keep it in picometers. Makes the math easier right now. So we would plug into this. So 4 times our 196 picometers, divide by our square root of 2, that's going to give us A. And you can punch it in, or you can say, sure, I did it. We get 554 picometers. So A is the length of the side. A is how far from here to here. So that's A. So this is our first step. Our second step is the length of the side equals 2 radiuses plus the space, or the gap, whatever you want to call it. So from this, A is from this bromine to this bromine, and it includes the space. So, does that make sense? If we take our A minus the 2 radiuses, we will get the space. So 554 picometers minus 2 times 196 picometers, and we'll find our space is 162. All right. So sodium ion is 98 picometers. That's the radius. So the question is, does it fit? And the answer is it does not fit. So why does 98 not fit into 162?
Too small?
Because it's a radius, and you're not fitting in half an atom. You have to fit in the whole sodium. So diameter, remember, is double that. So that would be what, 196? So it does not fit in the space. So when the sodium pushes the chlorides or the bromides apart. It makes the math easier. So along the edge, A is now equal to 2 radiuses of sodium plus 2 radiuses of the bromide. So we have this radius here, the bromide, this radius of this bromide, and then we go the whole way across the sodium. They're actually touching along the face, and so we just add them up. So 2 times the 98. And so just as long as you label your work, then you'll be able to follow your thinking. And 2 times 196, and that gives us 588. That is A. All right. If we know A, A cubed will equal the volume. before you cube it, change this to centimeters and then cube it. Otherwise, you have to cube that whole thing. But, all right, I'm just going to give you what the volume is because I'm tired. And so I know you all are tired too because you've all had midterms and stuff this week. Aren't you glad mine was over with last week? Right, so that's the volume. Questions. This is again when we get to Ionic. This is the last page of the lab. Is going to be math like this. The study set, I do it like the previous page pretty much. And again, the lab's not due this weekend. You get 2 weeks to work on it. So just remember you have these notes. So now we're going to do math. So the bromide is FCC. So there are 4 atoms. The sodium is going to be on the edge plus the center. And so it is also 4 atoms. That goes back to the very first page. So you have 1 center and 1 atom in the center and 3 along the edges. This makes sense because we would want the same number of each because we know sodium bromide, the formula is NaBr. So we know it's a 1-to-1 ratio. So it makes sense. There's 4 atoms or technically ions. We should say ions. Shame on me. So that means that there are 4 sodium chlorides per unit cell. Because
sodium bromides.
Oh, sorry, sodium bromides. Thank you. So what is the mass of sodium bromide? Like, sorry, sodium is 23, 79.9. So from the periodic table, we have 102.9 grams per mole of the whole sodium bromide. And then 1 mole is Avogadro's number. So a technicality thing on this, it is not technically atoms. These are called formula units. You can abbreviate it if you want. I'm not going to. And then there are 4 sodium bromide units, thank you, per 1 cell or for 1 FCC. So we punch that in, that will give us our mass. So 6.834 times 10 to the negative 22 grams per unit cell. And then we got one more step. The density, you would just take the mass divided by the volume. And we should get that number. So if you take our mass, so I'll give you a moment to write that in, the mass divided by volume. It'd be a 3-hour class, can you imagine? Rocky's like, aren't you done yet? So your mass divided by your volume. They're not both 22, are they? I think I wrote something wrong. Oh, they are. You should get 3.36. All right. So that is solid geometry. Questions before I stop recording?